Good morning. Okay, we are continuing with magnetic fields. We talked a little bit about permanent magnets. We'll talk more about them later. And we talked about forces that particles feel when they're moving in a magnetic field. Remember, a particle, a charge, we're talking about charged particles interacting with magnetic fields. And if that particle is at rest, where's my, there we go. If that particle is at rest in a stationary, a uniform stationary magnetic field, then it feels no force. If the particle is moving along the magnetic field lines, it feels no force. It has to have some component of its velocity perpendicular to the magnetic field lines in order to feel a force. So we talked about that. We used our right-hand rule. This is a cross product, remember. So cross product in the formula, we have a certain right-hand rule for determining the direction. If you hope you've been practicing that. I put my fingers in the direction of the first vector and then kind of roll them towards the second vector, and my thumb points in the direction of the cross product. Because it's perpendicular, the cross product is perpendicular to the plane that the two vectors lie in. So if we're doing A cross B, whatever plane is defined by A and B, by where they lie when you put their tails together, the cross product is perpendicular to that. What else did we do? And then we talked about currents. If a current is the flow of positive charges, moving charges feel a force, right? Due to this cross product of the velocity in the magnetic field. And we have to think about the sign though, remember, because our formula is, what's our formula? Okay, so a couple of things here. One is this, I know it's clear, crystal clear the way I draw my V's here. This is a lowercase v, this is velocity, not a capital V for electric potential, right? This is velocity. And the velocity of the particle, the magnetic field, the cross product gives us the direction of the cross product. If Q is positive, the force is also in that same direction. If Q is negative, then we flip it 180 degrees. The force is in the opposite direction. Okay. And then we said, remember, that we could think about current flow as the movement of positive charges in the direction of the current. That's the way we've been thinking about it in our circuits. Or we can think about it as the movement of negative charges, electrons, in the opposite direction, and the force is the same either way. The force is the same either way. We are going to see something, maybe today, maybe next class, I think today, we are going to see that there is some difference there. And because there's a difference, how the charges react, whether it's positive charges moving in one direction or negative charges moving in the other, there is a difference. The force is the same either way. The force is the same, but something else is different, and that is how our magnetic field sensor works. We'll talk about that later on. And that's another verification that it's the negatives that are moving in our metal wires and not the positive charges. Okay. Did I recap all right? We refresh your memory a little bit from what we talked about last week?
Certainly.
Okay, so let's get back to it. What we were talking about when we ended on Thursday or Wednesday was torque, right? Torque. So if this is my, if this is a current loop, this is a wire, a rectangular loop of wire, and I have a current coming up on one side and across the top and down and across the bottom, right? And I have a magnetic field. What direction should my magnetic field be? How about to the left? I have a magnetic field in this direction. So my current is going up on this side. What direction is the force? On this side, the current's going up. The magnetic field is to the left. So I cross B is toward the camera, right? Toward you. So this side feels a force toward you. How about the top? The top feels no force, right? Because it's parallel to the magnetic field line. How about this side? It feels a force toward me, away from the camera, right? Toward me. And the bottom feels no force, it's parallel. So there's no net force on this loop of wire. There's no net force on it. But one side is being pulled toward you. The other side is being pulled toward me. So what is there? There's a torque. It wants to rotate in the magnetic field. It gets twisted like this. So let's look at that. Yes. So we'll get to a different formula for torque that also uses a cross product right-hand rule. But for this one, what I said was I used. Let me sneak one more equation in here that we talked about last time. Right. This is for charged particles. And this is for current carrying wires. Okay. So what did I do for my loop of wire? I said the magnetic field is to the left, the current is up. I put my fingers in the direction of the current, rolled them toward the magnetic field. My thumb pointed toward you, toward the camera. So I expected this side to get pulled this way. And this one, I point my fingers in the direction, roll them toward the magnetic field. My thumb points toward me. So this side gets pulled toward me. It gets twisted like this. And there are a lot of different ways people do the right-hand rule for cross product. I point my fingers in the direction of the first vector and then roll them towards the second vector, and my thumb points in the direction of the cross product. Some people use sort of the three orthogonal fingers. Your index finger, I guess, will be the first vector, and your middle finger would be the second vector, and your thumb would be the cross product. Some people do a hand like this. I think it's the first vector is your fingers, the second vector is your thumb, and then out the palm of your hand is the cross product. Is that right? No, the first vector is your thumb, second vector is your fingers, and then out the palm of your hand is the cross product. So whatever you like to use, there are probably, a bunch of different methods for doing it. Just be consistent, use something that you like, stick with it. Remember, these all originate because there's a cross product in the formula. Okay, so it might seem like we have a dozen different right hand. We do have probably 3 different right hand rules, but a bunch of them fall under the category of cross product. So as long as you understand that it stems from a cross product, then it kind of tells you which one you have to use. All right, so let's look at the general case. We've got a loop sitting in a magnetic field, and we're going to be doing a top-down view. So if this is the loop, if the magnetic field is to the left and this is the loop, we're going to be sort of looking down at it this way. We got the magnetic field is to the left, and the loop is going to be at a little bit of an angle. Last time we did it where it was aligned with the field, but that's kind of a special case. We're just going to pick any arbitrary angle like this and do a top-down view. We know from the side it looks like this when you're looking at the face of the loop, but we're going to look down at the end from the top, and it's going to look like that. So here's our top view. Our magnetic field. I've got it going to the right here, but that's okay. And we've got our loop of wire at some arbitrary angle. A current, let's have the current coming up on this side and down on that side. So what direction is the force on this side over here? What direction is the force on that side of the loop? What I mean is that the current is flowing around this loop of wire, right? This is just represents a rectangular loop of wire. The current is going around in some direction, right? So if we are looking down at the top, one side, the current is coming toward us, then it goes across, and on the other side, it's going away from us, right? It's those two sides that are coming toward us and away from us, right? When we tilted it like this, those were the two sides that were feeling the force that was causing the torque. The other two sides weren't causing any torque. So, oops. If we just look at this picture, the current is coming out of the page, the magnetic field is to the right, so my thumb points toward the top of the page. What's going on? Come on, there we go. And if you do the same thing on the other side, so what would the top and the bottom of the loop be doing? Let's go across the top. So the current came up this side right here. Now what's it doing? It's going across. It's going across the top of the loop. Looking at my diagram here, the current came up this side. Now it's going across the top. So when we're looking at it, it came up this side towards the camera. Now it's going across the top. So what happens? What's the force when it's going across the top? Out of the page is correct. So I've got this thing sitting here. The current is coming toward the camera on this side, and the force is, I guess I have to, I drew my magnetic field on my paper going to the right. So let's reverse, I'll just keep with what I drew on the paper. So my magnetic field is going to the right. My current is coming toward you on this side. So the force would be up. It's being pulled up like this. But the one going across this way, when I do I cross B, I get the forces toward the camera. So is that doing any torque? That's just pulling the loop toward the camera. It's not twisting it at all. And then the one on the other side is pulling the loop away from the camera. So those are just tugging on the loop. One's pulling it toward the camera, one's pulling it away from it. But it doesn't change the rotation at all. It's not doing anything to cause it to rotate. Those just cancel out. They don't create a net force. They don't create a torque. They just cancel out. The one going away from you, that's what we're going to do next, is going to be in what direction? Toward the bottom of the page. Yeah, perpendicular to the wire. Did you get that? So we've got a current, the loop started like this, current this way, across the top, toward me, across the back. There was a force in this direction. The loop started to rotate. Now we've taken this snapshot. What you see on my screen right now is a snapshot. The loop's rotated a little bit, and the force, instead of being perpendicular to the loop of wire, the force is still pointing straight up. So what's going to happen as this loop continues to rotate? It's going to get to this point, right? Let's draw that next. The loop's rotated a little bit. And this upper one, the force is still toward the top of the page. And the lower one, the force is still toward the bottom of the page. You follow me? It started like this. Force up on this side, down on this side. It started to rotate. Then we took a snapshot as it was rotating. That's the picture you see on the screen right now. The force, instead of being perpendicular to the loop, is at a funny angle because it points straight up, right? I cross B is still straight up. And then a little bit later, the loop has rotated to this point, and now the force is still straight up, right? I is toward the camera. B is to the right, so I cross B is up. So this top of the loop is being pulled up, the bottom of the loop is being pulled down. What's the torque at that instant? 0. There's no torque at that instant. The loop isn't being caused to rotate. If I started with my loop like this, it would never rotate, it would just stay like that. But I didn't start with my loop like this. I started with it like this. So it started to rotate. And what's it got? Inertia. It's going to keep rotating. And it's going to go right past that point. We'll draw that next. And when it goes past that point, let's go a little later. Should probably draw a Oops. And a little bit later, what's it look like? It's over here now, right? And the force on this guy, so our torque now is in what direction? The other direction. So the loop now is going to start slowing down and it wants to go back to in the other direction. So it will oscillate back and forth. If I started with my loop like this, it'll start to rotate. At this instant, there's zero torque, but it has inertia, so it keeps going. Now the torque is in the opposite direction, so it slows down, slows down, slows down, and then it flips back and it'll rotate in the other direction. And what's it going to do? It's going to flip and flop back and forth like this, rotating back and forth like a pendulum, right? Like some kind of oscillator. If you pull a pendulum up to one side and you let go of the pendulum, there's a net force acting on it, right? And the pendulum starts to swing down. And when the pendulum gets to its lowest point, it has zero net force acting on it right there. But that's when it's moving the fastest and it has inertia. So it keeps going through that point. And then once it starts going in the other side, there's a force in the opposite direction. It slows it down until it comes to rest momentarily. And then the net force is back towards the equilibrium position. So it starts to go back that way and it oscillates back and forth. The pendulum oscillates back and forth like that. And that's the same thing that would happen here. You start with the current, it's going to cause a torque. But when it gets to the halfway point here, the torque is zero. And when it passes that point, the torque is in the opposite direction, slowing it down and then causing it to flip back. And then slowing it down and then causing it to flip back. And it'll oscillate like that, back and forth. That's a good question. Is there a simulation for this? I have to look. I have to check the PhET simulators. There are probably some, maybe not for a whole current loop, but probably for a current. I'll have to look. Yes, yes. Okay, let's talk a little bit about the math. So we'll pick just some angle, right? Any angle. Trying to figure out what the torque is. This is our magnetic field. The torque is going to be the force times the lever arm. And the lever arm, in this case, if this is the halfway point, this is it was, I called one side of my my rectangle W, remember? This is a top view. So that's half the width of my rectangle times the sine of theta, where theta is this angle. And this is what we call the area vector. So this turns out to be okay, so we're looking at a force and a lever arm. A force and a lever arm. You have to kind of refresh your memory about torque from physics 4A. And this is equal to I, A, B, sine theta. Remember, we did it last time when the loop was aligned with the magnetic field, and we just got I times A times B, where A is the area of the loop. Well, if we write this out, we can write this out as a cross product. The torque is a cross product, the area vector I times the cross product of the area vector and the magnetic field. So the area vector, how do we define a plane with a vector? We pick the normal to the plane, right? Something perpendicular to the plane. That's how we define a plane usually with a vector. So the area vector is normal to the loop of wire, the plane that the loop of wire lies in, and its magnitude is equal to the area of the loop of wire. Now the direction, we have another right-hand rule. Okay, so this is a different right-hand rule. The direction we get for the area vector, we run our fingers around the loop of wire. Here's my loop of wire. If my current is going up on this side, across, down on this side, and across this way, if my current is going that way, that would be what, clockwise current? I wrap my fingers around the loop of wire in the clockwise direction, and my thumb points in the direction of the area vector, and I use my right hand. So if the current was going in that direction, the area vector would point toward me. If the current was going up on this side and down on this side, I would wrap my fingers that way, and the area vector would point toward you. Okay? So this is a different right-hand rule. And then we have our torque comes from a cross product. So you have to remember back to physics 4A, how do we define torque? Torque is a vector that points along the axis of rotation, right? So A cross B, if we look at our diagram here, A kind of points up and to the right, B points to the right. So my A cross B points into the page. You see that? A cross B is into the page. And what does into the page mean? You take your right hand rule and you stick your thumb into the page, and your fingers tell you that this object is going to rotate clockwise as you look down on the page. This is just a refresher from 4A, how we define torque as a vector along the axis of rotation, and our right hand rule tells us what direction it's going to rotate. Okay, so there's one more thing we do here. We define a magnetic dipole moment. A lot of books do this. Mu as the current. I don't know why we do this, but we do it. the current times the area. We call that the magnetic dipole moment. Yes, right-hand rule. So in this equation here, we actually sort of have two right-hand rules we're using. One of them tells us what direction the area vector points. So let's say I have this loop of wire here. The current is going toward you on this side, across and away from you. And my magnetic field points to the right. So first thing I would do, I'd wrap my, remember the current is coming toward you on this side and away from you. I'd wrap my fingers around the loop of wire and the area vector would point up from this, right? It's coming toward you on this side and across and back. So I wrap my fingers around it and I get the area vectors pointing up. If I had the loop of wire this way with the current going up this side, I'd wrap my fingers around like this, it would be pointing toward me, right? But as I rotate this around so we can look at it this way, I see that it's really pointing up when I do it now. So I've got an area vector pointing up and I've got a magnetic field pointing to the right. So now I use a cross product, area vector, cross product with B, and I get the torque points toward me. So that tells me that the axis of rotation is pointing from me to you, you to me, and the torque points away from you toward me, away from the camera toward me. And that means that this thing is going to rotate that way. It's going to rotate that way. Okay, so our torque, we're trying to get to a general formula here. We're not quite there yet. The torque is, we could write it as mu cross B if you'd like, but this is for one loop of wire at one turn. Oftentimes we want torque. Think about electric motors. You run a current through a loop of wire. You see where we're going with this? You run a current through a loop of wire sitting in a magnetic field, and what's it do? It turns. That's an electric motor, right? So with an electric motor, you want torque. You want that thing to turn and turn whatever it is that it's hooked up to, right? Your DVD drive or the wheels in your car or whatever it is it's hooked up to. So you want a lot of torque. You might not just want one loop of wire. You might take your loop of wire and go around and around and around and around. And that way, when you turn the current on, instead of having one current loop, you have a whole bunch of current loops. And each turn, each loop of wire is flowing the same current, and each one feels the same torque. And you've just multiplied the torque by however many loops you have there. So we can do the same thing with our equation just by adding an n here. The torque is equal to n times mu, where n is the number of turns. This one will oscillate. Yes, this one would not be a very good motor. But there are some tricks we can do that will make it a motor, to make it keep going around. Okay, let's keep going. So just real quick, loop of wire carrying a current I. The right-hand rule. The right-hand rule gives the direction of A. What direction would it be in this case? Out of the page. Okay. All right, let's just run through a quick, let's just recap. Let's see, I've got a magnetic field. And I've got a loop of wire that lies in the same plane. Everything's in the plane of the page here. Going to flow a current into my loop of wire. It's going to go around and come out over here. Let's call this side 1. And 2, and 3, and 4. We good? Question about the last one? We don't need B. We are just defining the area vector for the loop of wire. The area vector points out of the page. Now, if I gave you B, I could say, is there torque and what direction is the torque? For torque, you need B. But just to define the area vector, you just need the loop and the direction the current is flowing through it. Okay, let's look at each side. Force on side 1. I'm calling side 1 the whole bottom part because it's going to be the same on each side, right? Zero. Force on side 2, what direction? I shouldn't have an equal. Is. Into the page, right? Yes. Side 3. And side 4. Out of page. Hopefully you're following that. If not, we can go over right-hand rules. So the net force on this loop of wire is 0. But the net torque I'll just use a, is not 0. What direction is my area vector? Into the page. The net force is 0 because you have F2. What's F2 equal to? I could have written it out there. F2 is F2 is the current times the length of this side times the magnetic field, right? And what's F4 equal to? The current times the length of that side, which is the same as the length of side 2, times the magnetic field, which is the same magnetic field that side 2 is in. So you have ILB in one direction, you have ILB in the other direction. Add them up, you get 0. And so what direction is my torque? Because they're being applied at different places, right? So you have a force, you have a force on this side that's up, you have a force on this side that's down. Well, those two forces add up to 0. There's no, this object isn't going to start moving, right? One force is pulling it up, one force is pulling it down. The center of mass of this object is never going to move. It's going to stay at the exact same place. The center of mass isn't going anywhere. But because the forces are offset from each other, there's a net torque. They're going to cause it to twist. And using our cross product, area vector cross product with the magnetic field, the area vector is out of the page. The magnetic field is to the right. So I get the area vector, sorry, is into the page. Area vector is into the page. Magnetic field is to the right. I get towards the bottom of the page. Yes. Okay. How about we rotate this loop by 90 degrees and we do it one more time. So the loop here is in the plane of the page. So my magnetic field will be exactly the same. And I'll use my artistic ability to draw a loop here that's perpendicular to the page. I'm sorry, I'm artistically challenged. There we go, kind of sort of like that. So we've got a current that comes up this side. This is side 1. This is side 2. This is side 3. This is 4. And I'm calling this 1 again, right? So one is going, what are the directions? So if the loop of wire is perpendicular to the plane of the page, I've sort of drawn it at an angle like this, but think of it as being perpendicular to the plane of the page. F1 would be toward the top of the page. You see that? F2 into the page. Okay, so what do we have here? We've got a magnetic field to the right and a loop of wire perpendicular to it like this, right? Perpendicular to it. Magnetic field to the right, loop of wire like this. So side one is coming toward you, right? Out of the page would be toward you. The current's coming toward you on the bottom here, right? Toward you. So if the current's going toward you and the magnetic field is that way, I cross B is up. So the bottom, the current's coming toward you, magnetic field's to the right, the force is towards the center of the loop or up. Then on the side that's closest to you, out of the page here, the current's going up, that's side two, current's going up. And I put my fingers in the direction of the current and I roll them toward the magnetic field and my thumb points away from you, right, into the page. Towards you is out of the page, toward me is into the page. Towards the center of the loop, actually. And then the top is coming into the page or away from the camera. So I is pointing that way, B is pointing that way, I is toward me, B is to the right, my thumb points down toward the bottom of the page, or actually in this case, toward the center of the loop. Okay, and now I'm on this far side, the side four that's in the page. The current's going toward the bottom of the page. So I put my fingers that way, but the magnetic field is to the right. So I turn my hand around so my fingers are pointing in the direction of I, and I roll them toward B, and my thumb points out of the page toward the camera. So side four would be out of the page. Did that help a little bit? You know, get a little book or something and use it as if you need to, rather than trying to just look at pictures. You know, get a little book and hold it up and say, this is my loop of wire and the current's flowing this way, and you know, it helps you visualize in three dimensions. All right, so our net force has to be, anytime we have a current carrying loop of wire in a uniform magnetic field, the net force will be 0. Why is that? Because the opposite sides of the loop, the magnetic field strength is the same on the opposite sides of the loop. The length of the wires are the same. And so what do we get? we get equal and opposite forces because the current direction is opposite, right? Equal and opposite forces. Now, if the magnetic field is not uniform, if it changes over the distance, then one side of the loop is in a stronger magnetic field than the other side, and we do get a net force on our loop. But we'll talk about that later. Okay, let's just finish this up, and then we'll take a little break. So the net force is 0. How about the net torque? What's our net torque in this case? 0 or non-zero? 0, because every side, losing my voice, every side of my loop is being pulled toward the center of the loop. Every side, the force was in. So if every side, the force is toward the center, then it's not going to cause this to rotate at all. Or if every side is out, sometimes you can set it up where every side feels a force. If I just reverse the direction of the current, right, every side would feel a force out. So the loop's just getting pulled, but it's not gonna rotate at all. So in this case, we have 0 torque. What's our area vector? Let's just confirm that by doing A cross B and see what we get. Hopefully 0, right? Because the torque is A cross B. Our area vector is what direction? To the left. Because what do? I wrap my fingers around the loop in the direction of the current, and my thumb points to the left. If the area vector points to the left, and the B points to the right, then what is A cross B? What is the torque? It's 0, right? Because A is pointing this way and B is pointing that way, and the sine of 180 is 0. Yes. Yes, it should. I mean, that's the formula for torque. It should give us 0. But where is it coming from? It's coming from the force on each side. So if you go back and you look at the force on each side, you should be able to reason out that there's no torque. Okay. Good time for a 10-minute break. All right, let's take a 10-minute break. All right, we're back. Let's look at some examples of where this is used, because it's you're probably familiar with some of these things. So let's maybe from chemistry, where you've used a mass spectrometer. So let's talk about some of the applications here. But first, just a quick recap of a particle moving in a magnetic field, a charged particle moving in a magnetic field. I'll make my magnetic field into the page. got a charged particle over here. What direction is the force on my charged particle moving to the right in this magnetic field? Towards the top of the page. So the particle ends up moving in this path. Eventually, it ends up over here. At that instant, it's moving in this direction. And what direction is the force on it when it's at that location? V is towards the top of the page. B is into the page, so my thumb points to the left. Right, at this instant, so what do we get? Circular motion. What do we know about something that's moving in a circular path? We know the net force in the radial direction. Has to equal some special value we call the centripetal force. And what is that? That is mv squared over r. All right, and what is the net force in the radial direction? There's only one force. It's the magnetic force, F sub b. So that has to be mv squared over r. And F sub b, what do we know about F sub b? It is Q V cross B. So look back up here, what do we get? Q times V times B times the sine of 90 degrees, which is 1, right? So this is just Q V B. And over here we have m v squared over r. So we get the radius, I guess we could solve for anything, but the radius is mv over qb. Right, if you think about, let's fix those four variables. We got our mass of our particle, the charge of the particle, the velocity of the particle, and the magnetic field it's moving in. So if we fix them all, we've got it moving at a certain radius. And if we were to magically increase the magnetic field, what would happen? the force would be bigger, pulling it towards the center. So it would want to rotate at a smaller radius. If we magically increased the charge from our original condition, we magically increased the charge, the force would get bigger. It would want to rotate at a smaller radius. Does that make sense? Same with mass and velocity, right? If everything was constant and we magically increased the mass, it would move to a larger radius. It would want to move at a larger radius. It would take a bigger force to keep it moving at that radius. So it would have to move, if we kept everything else the same, it would have to move to a larger radius. And the same with velocity. Okay, kind of makes sense. So how do we use this? One application is the cyclotron. Since we're in the Bay Area and the cyclotron was invented at UC Berkeley, we'll talk about it a little bit here. What they have, this is used for accelerating charged particles, get them go faster and faster and faster. Physicists, one of the techniques they have for understanding fundamentally what's going on inside of a particle is to try to look inside of the particle. So the analogy that they use a lot with high energy physics is if you wanted to know how a watch worked, right? You can look at it from the outside, but you'll never really understand how it works. But if you take that watch and you throw it against the wall as hard as you can, and it breaks apart, and you can see that the watch is made up of springs and gears and things like that, then you can kind of understand, oh, wait a minute, now I can see there's springs in here, there's gears, I can wind it up, I can do this, maybe there's even a battery in there. Some watches, right, have batteries in there. Now you kind of start to understand about what's going on inside that particle. So physicists wanted to take particles and slam them into things and break them up and see what they're made of. So that was the idea here. How do you accelerate a particle so it goes fast enough so you can slam it into something and break it into pieces? So what they have are two, they call them Ds because they are D-shaped regions, like the letter D, a capital letter D, regions with, that's one. And there's another one. It's not very symmetric looking, are they? Is that better? It's getting worse. Okay, there we go, close enough. Two D-shaped regions with magnetic field. I'll make my magnetic field coming out of the page. So there's our B. And there's another region here, similar magnetic field. And these two plates right here, they hook up an alternating potential. So that's, remember, we've talked about it briefly, but that's the symbol we use for a potential source, like this is the symbol we use for a battery, right? A DC source, one that has constant potential difference. But this other symbol, the sine wave, right, is what we use for a potential source that's alternating or changing in time. So that's what they've got there, some kind of an alternating potential. Then you take your charged particle and you release it right in the center. So you put a charged particle, I use red, I guess. I'll make it a positive charge. You release a positive charge there at the center, and there's a potential difference. So there's an electric field there. An electric field accelerates that charged particle. Let's say it happens to make it go up. So the charged particle gets accelerated upward. It passes through that material, and now we have a charged particle moving in a magnetic field. So it feels a force in the radial direction that keeps it moving in a circular path, and it's going to move something like this, right? So far, so good. Now it gets back to this center section where there's a potential difference. But by the time it gets back there, the AC source has flipped. The potential difference is flipped. And now the electric field is pointing in the opposite direction. So it gets accelerated through this region. And then it leaves the electric field, and now it's just moving with constant speed in the magnetic field, and it feels a force, but it moves with a bigger radius this time because it's going a little bit faster now, right? So it moves with a bigger radius. So it ends up over here. And by the time it gets back to this region where we have our potential difference, where we have our electric field, we've flipped the potential. And now the field is pointing up again, and the particle gets accelerated up because it's a positive charge. And now it hits this other region of magnetic field going a little bit faster than it was before. So it moves in a circular path with a larger radius than it did last time. And by the time it gets back to this region, it's going a little bit faster. It gets accelerated. The potential difference flips again, and it gets accelerated down. Now it's moving even faster, right? And a bigger radius. Now it's over here. And by the time it gets back to that region, those potential has flipped again. So the electric field is pointing up, and it accelerates it, gives it a little push. And then it comes around with a bigger radius, and it leaves moving at some high speed, okay? The first cyclotrons that they invented at Berkeley would fit in the palm of your hand. They were a couple of inches in diameter, and they kept making bigger ones and bigger ones until they had, I think, a couple of meters in diameter. Those are the big ones they have there. And then they realized that keep causing a particle to go in a circle, it actually radiates a lot of its energy when it moves in a circular path. And so there's kind of diminishing returns there, and it's better, once you get it moving at a certain speed, you're better off accelerating it in a linear fashion. So they've gone to linear accelerators. Stanford has the linear accelerator there, SLAC, Stanford Linear Accelerator Center. When you go up Highway 280, you drive right over it. It's just a few miles up the road from Foothill. Okay, so this is how a cyclotron works. Now, you might be wondering, how do they flip it every time the particle happens to be right there at that region, that center region with the electric field? How can they get that right? Well, the answer is that it takes the same amount of time. Every one of these curved half circles takes the same amount of time for the particle to go through it. The radius is bigger, so the distance covered is much bigger each time, but the speed is bigger, and they exactly offset each other because the radius is proportional to the speed. So the distance is proportional to the speed. So as they increase, the time stays the same. So that alternating potential that you see there, it flips at a fixed time interval. And the particle will, you pick the frequency that you need, but the particle always hits that region where the electric field is in the same time interval, because each one of these circular half circles of path through the magnetic field takes the same amount of time for the particle to travel through it, whether the radius is small or whether the radius is big. Okay. That's a cyclotron. Let's talk about a velocity selector. Oftentimes, when you're creating particles with velocity, you get a whole range of velocities. You don't just get them coming out at one velocity, but you might want a very, very particular velocity. You might not want a range of velocities. You might want a real narrow region. So if we have a source here that's creating particles with some velocity, that's producing charged particles with different velocities. And they're shooting out here like this. What we can do is run them through something called the velocity selector. The velocity selector has an electric field in one direction. Right, it creates an electric field in one direction. I'll use green for my electric field. And we have a magnetic field in another direction. I'll use blue. The particle comes through that region. Let's say our particle is positively charged. What direction is the force due to the electric field as the particle moves through that electric field? In the same direction as the electric field, right? What's the force due to an electric field? It's QE. If the particle is positively charged, the force is in the same direction as the electric field. Good? What's the force due to the magnetic field? V is to the right, B is into the page. So my thumb, when I do the cross product, points toward the top of the page. That's correct. That's Q times V times B. One of these forces depends on the velocity, the magnetic force. So we can tune this. What we really want, if QE is equal to QVB, then what happens? The particle goes straight through, right? If it's going too slow, what happens to it? The magnetic force is smaller. So the particle ends up heading towards the bottom of the page, right? So too slow, and the particle goes that way. You see that? Because this has a V in it. As V gets smaller, that force gets smaller, but the electric force stays the same. If it's going too fast, the magnetic force gets bigger, but the electric force stays the same. So where does it go? It goes up. So we can build a wall over here with a hole in it. And what's going to make it through? Only the particles that have just the right speed. If the speed is just right, the particles can make it through the slot in the hole there. And what is that speed? We get the velocity is equal to the electric field over the magnetic field. That's velocity. Okay. Now, you might put one of these on a mass spectrometer, and maybe you used a mass spectrometer in chemistry. So what would you do? You'd have your source, your ion source. Spitting out charged particles. And you'd probably have a velocity selector as part of that. So you'd only have a very particular velocity particle hitting your mass spec. And we have a magnetic field up here. I'll just make it coming out of the page. So what happens when your charged particle hits that region of magnetic field? It moves in a circular path. And here's our detector over here. If the mass is just right, because remember, where's our formula for, oh, here we go. Formula for the radius as a particle moves in a magnetic field. We've used a velocity selector, so all the particles are coming in with the same velocity. Our magnetic field is fixed, right? And our Q, they all have the same charge. They're all singly ionized or whatever it is. They all have the same charge. So the only thing that affects the radius now is the mass of those particles. So if the mass is just right, it follows the arc and hits our detector. And if it's too light, it spins in with a smaller radius, doesn't hit the detector. And if it's too heavy, too massive, it follows a larger radius, right? Because R is mv over qb. That's an R. Yeah, clever applications. Maybe you've used the mass spec, hopefully. All right, so those are a few. Now let's, one more thing I want to talk about is our Hall effect probe, because this is how we've used a magnetic field sensor in lab. Well, you watched a video of me use it in lab when I measured the magnetic field in the slinky, right, in the solenoid. I used a magnetic field sensor, and you might have wondered, how does that magnetic field sensor work? Well, I'm going to tell you right now. It works based on the Hall effect. And this also is important because it tells us that charged particles, that the negatives are really the ones that are moving. We get a different result if it's the positives that are moving or the negatives that are moving. So let's look at what happens here. We have a conductive ribbon. We usually use a wider, not just a wire, but something a little wider than that, like a conductive ribbon. And it's in a region of magnetic field. Just make it going into the page, how about? And it has some thickness to it, T. What happens as the charges move through the magnetic field, positive charges get pushed in one direction, and that leaves negative charges behind. And so you get a delta V across across from one side of that ribbon to the other. If you put a voltmeter there, you would actually measure a voltage difference. So let's take a look. If negative charges move, what does that mean? That means that a current to the right is actually negatives to the left. So here's our magnetic field region. Here's our ribbon. We have negative charges moving in this direction. What direction is the force on those negative charges? Toward the top of the page, that's correct. Because V V cross B is towards the bottom of the page, but it's a negative, so that flips at 180. So the negatives would be up here. And what does that leave behind? Leaves behind the positives. And so if we got our voltmeter out and measured the voltage across that ribbon, the bottom would be at higher potential. What direction is the force on this ribbon? Towards the top of the page, right? Now let's take a look at if the positive charges are really moving. That means a current to the right is positive charges moving to the right. So our region of magnetic field, our ribbon of our conductive ribbon here, we have a positive charge moving to the right. What direction is the force on this positive charge? Up. Positives end up here. I'll use red. That means there's a force up. Remember, we already went through this. The force on that wire is the same, whether the positives are moving to the right or the negatives are moving to the left. It doesn't matter. The force on that wire is the same. It's towards the top of the page. But the potential difference between the top of that wire and the bottom is opposite. It's different, whether the positives are pushing the wire up from the top or whether the negatives are pushing the wire up. So we hook up our voltmeter here. And now it would measure the top. So this is one more confirmation that the negative charges okay? Negatives move. And how does this thing work? The delta V that it measures, the Hall effect, is the current, the magnetic field, the thickness, and some constant there. So you can figure out the magnetic field from these other variables. Don't worry about the formula. I'm not going to ask you to anything with this formula, but conceptually understanding what's going on is kind of nice. One, because we actually use this in lab, and it's a good idea to understand how it works. And two, because it's confirmation that negative charges are actually what's moving in our circuits. Okay. We have been talking about charges and how charged particles interact with magnetic fields. That's what we've been talking about the last couple of days. And what we're going to do now is start to look at how charged particles create magnetic fields. Charged particles, when they move, they fill the space around them with a magnetic field. This was actually discovered by accident. If you have a current carrying wire, let's say right here. So no, this is a wire with no current, perpendicular to the page. And we've got some little compass needles around. And where are they pointing? Towards the North Pole of the Earth, I guess. Now we turn on a current. And what happens is those magnetic field sensors, those compass needles, turn and align themselves in this orientation. Okay, that's when we turn the current on in that wire. So the current is coming up out of the page. What happens is we get magnetic fields that form circles around the current carrying wire. The magnetic fields form in circular lines around the current carrying wire. If we were to draw the magnetic field around that wire, it would look like that. And this brings us to a right-hand rule we have for figuring out the direction of that magnetic field. The first thing you have to recognize is that the magnetic fields form circles around the wire. Okay, once you've come to that, once you've come to grips with that and you're okay with that, then the question is, what direction is the current going, right? So if I have need some props. If I have a current carrying wire here that's carrying current toward the camera, toward you, I know that there's a magnetic field that forms a circle around that current carrying wire. I don't know whether it's clockwise or counterclockwise, but I know it's a circle. So I take my right hand, another right hand rule, and I stick my thumb in the direction of the current. And my fingers wrap around the wire in the direction of the magnetic field. So if the current is going toward the camera, toward you, you would say it goes counterclockwise around the wire. If the current is going away from you, toward me, I take my thumb and I stick it toward me, away from the camera, and my fingers roll around in a clockwise direction, right, around the wire. So that's the way I drew it here. I got my thumb coming up out of the page because the current right in the middle there is coming out of the page, and my fingers are wrapping around in the counterclockwise direction. So I drew my magnetic field in the counterclockwise direction. Now, of course, the magnetic field is going to drop off as we move away from this wire. So if I drew it more carefully, let's draw the current into the page. If the current is going into the page, then my magnetic field is going to be clockwise around it. I'll use blue. Something like that, right? As we move away from that current carrying wire, the magnetic field gets weaker and weaker. It drops off. Are we going to look at why the magnetic fields form with the motion of charged particles? No. We'll take it, we'll just accept it. So we sort of say that all magnetic fields originate from the motion of charged particles. And one way to do that, like in an electromagnet, you turn on a current and that forms a magnetic field. And the nice thing about electromagnets is you can turn off the current and the magnetic field stops. So they use those in junkyards. You've seen movies, right, where they pick up a whole bunch of metal, they turn on a magnet, pick up a whole bunch of metal, and then they just turn off the magnetic field and all that metal falls off, right? So it's a way of moving metal around. Easy way to turn on and off a magnet is use an electric magnet. Or we have permanent magnets, and in those cases, you know, we sort of say it comes from the motion of the charged particles. That's really not technically correct. But at some level, on the atomic level with the electrons, they either have a magnetic moment or their orbital motion about the atom causes the atom to be magnetic. All right. So this is a good stopping point. We will have a lab at 12:15. So we'll have lab this week and next week, and then we'll skip. We're only going to do 8 labs. So that'll be 7 will be this week, 8 will be next week. We'll skip the last week of the quarter because we've got a lot going on that week anyway. We've got an exam, and then the very next week is finals. And so there's a lot going on. I think that's a good week to skip a lab. So lab today, lab this week. I haven't posted anything yet because I haven't finished the videos. So before my office hour, I hope to have everything posted online. But we'll talk. I can still walk you through some things during the lab. Okay. I'm going to go ahead.
Could you just quickly explain how you got the VH formula? The one where you say, tell us the negative charge are actually moving in our typical medical.
Oh, I didn't. I didn't. That comes from, let's see, you need the current, the force, what happens is you're going to end up with the charges are going to keep moving until they stop. So you've got a magnetic force. So you got a positive charge. Let's just pretend it's a positive charge moving this way. It doesn't matter. Positive charge moving this way, magnetic field into the page. It feels a force in this direction due to the magnetic field. So charges start to move, right? They start to pile up along there, and you're going to have a lack of positives here. Well, what does that do? That creates an electric field in the opposite direction. So the first particle starts to move and it feels a force and it ends up here. The second particle starts to move and it feels a magnetic force pushing it up, but it feels a repulsion from the one that's already moved. But the magnetic force is bigger, so it goes up, right? And the third particle feels a force from the magnetic field pushing it up and a force pushing it down from the two positives that are already there, right? But the magnetic force wins, so it goes up. Well, that keeps happening until the magnetic force doesn't win anymore. They equal each other out. And then what happens? The particles just go straight through. And we're left with some positives at the top and some negatives at the bottom. And they create an electric field that exactly cancels out the magnetic field. So if we look at the forces here, we get QE is equal to QVB, right? That's what we would get. It's just like the previous example with the velocity selector. And so what is the electric field? The electric field times this distance, T, is equal to delta V, right? The potential difference is the electric field. If the electric field is uniform, it's the E times the distance is the potential, right?
Okay, yeah.
So this is, E is really delta V over the thickness. And then you can turn velocity into current, you know, by changing a few things. And where is our formula? So that the thickness comes down. Oh, wait a minute. What did I do? Why is my thickness there? I think because it comes in when you change velocity into current, then you get some constants and you get the that depend on the material, right? The resistivity of the material and stuff like that. And then I think a thickness comes into play there too. And so that's why you end up with a T on the denominator on the other side. Anyway, if you start with this and then you transform velocity into current, you end up with that equation.
All right. Okay. Thank you.
Don't worry about the details.
Okay.